Welcome to our cosmic journey into the subatomic realm, where we'll unravel the mysteries of one of the universe's fundamental building blocks, the electron. These tiny particles, with a mass over 1,800 times lighter than a proton, are the workhorses of our electrical world. They power our homes, our devices, and even the neural pathways in our brains. But here's the thing, not all electrons are created equal. Just like there are different types of stars, each with unique properties and evolutionary paths, electrons also come in a variety of flavors, each with its own story to tell. We're going to embark on a deep dive into the fascinating world of 26 different types of electrons, exploring their unique characteristics, their governing equations, and the incredible roles they play in the cosmos. From free electrons roaming the vastness of space to bound electrons trapped in the embrace of atomic nuclei, we'll uncover the secrets behind these subatomic wonders. Get ready to expand your understanding of these fundamental particles because we're about to unlock a deeper level of the universe's intricate workings. Fasten your seatbelts, fellow knowledge seekers. It's going to be an electrifying ride. Our first stop on this subatomic safari brings us to the free electron. Imagine a lone traveler unburdened by any atomic nucleus, free to roam the cosmos. That's our free electron, a solitary particle carrying a negative charge, zipping through the universe. What governs these free spirits? The laws of electromagnetism. Maxwell's equations dictate how electric and magnetic fields interact with charged particles. This interplay determines the electron's trajectory and interactions within the universe. From the unfettered freedom of the free electron, we now turn our attention to its more restrained counterpart, the bound electron. Unlike their free-roaming cousins, these electrons are tethered to the nucleus of an atom, held captive by the electromagnetic force. These electrons are key players in determining an atom's chemical properties and interactions. Governed by quantum mechanics, they exist on specific energy levels, like steps on a staircase. Electrons jump between these levels by absorbing or emitting energy, creating the colors we see. These transitions follow specific rules, forming bonds that create molecules and complex structures. Welcome back, fellow travelers through the cosmos of subatomic particles. In this chapter, we're focusing on the valence electron, a term pivotal to understanding how atoms interact, bond, and essentially, how chemistry happens. Think of an atom like a bustling city. At its heart lies the nucleus, the dense downtown housing protons and neutrons. Zipping around this nucleus are our electrons, residing in specific energy levels or orbitals like neighborhoods in our city. Now the valence electrons? These are the folks living in the outermost suburbs of our atom. They're the ones most likely to interact with the outside world, other atoms to be precise. Why? Because they're furthest from the nucleus, less bound by its attractive forces. These interactions, my friends, are what lead to chemical bonds. Whether it's sharing electrons in covalent bonds or giving and taking them in ionic bonds, it's the valence electrons orchestrating this intricate dance of attraction and repulsion that governs our universe's molecular diversity. Let's shift gears now and talk about electrons on the move. You see, in the realm of electricity, it's the conduction electrons that take center stage. These aren't bound to a single atom, they're free to roam like cosmic nomads throughout a material. Imagine a copper wire, for example. Within that wire, a sea of conduction electrons exists, ready to flow in response to an electric field. Think of it like a highway, with electrons as cars, all prepared to move in unison. This collective motion, this flow of charge is what we call electric current. It's what powers our homes, our devices, our modern world, and it's all thanks to the remarkable freedom of these conduction electrons. Having ventured into the bustling suburbs of valence electrons and the open highways of conduction electrons, we now delve deeper, towards the heart of the atom, to meet the core electrons. As the name suggests, core electrons occupy the inner shells of an atom closer to the nucleus. They're tightly bound by the strong attractive force of the positively charged protons residing in the nucleus. Now, unlike their more adventurous counterparts, the valence electrons, these core electrons are less interested in forming bonds or conducting electricity. Their primary role is to maintain the stability of the atom itself. They're like the bedrock, the foundation upon which the atom's structure is built. They're influenced, of course, by the electromagnetic force of the nucleus, but they're not as easily perturbed as the valence electrons. Friends, we've all basked in the warmth of our nearest star, the sun. It feels good, right? But did you know that same sunlight is literally knocking electrons off of atoms? We call these liberated particles photoelectrons, and they're the foundation of things like solar panels and digital cameras. Einstein won a Nobel Prize for figuring this out, by the way, not for relativity. And that, my friends, is the power of the photoelectric effect. The universe seeks balance from falling apples to black holes. Atoms feel the same way. When an atom loses an electron, it rearranges to relax. Electrons drop to lower levels, releasing energy. Sometimes this energy ejects another electron. This is the Auger electron, named after Pierre Auger. Studying Auger electrons reveals atomic structure. We often think of electrons as tiny particles orbiting the nucleus, like planets around a star. But electrons can also shoot out from the heart of an atom, the nucleus itself. It sounds crazy, right? Like a car transforming into a motorcycle. This is the world of radioactive decay, producing high-energy beta particles. Beta decay happens when a neutron transforms into a proton. This transformation releases energy and a high-energy beta particle, an electron. These beta particles move at a significant fraction of the speed of light. They're like tiny missiles, ionizing matter in their path. Beta decay and high-energy electrons play crucial roles in natural processes. The universe is full of surprises where even atoms can transform dramatically. Greetings, fellow travelers through the cosmos of knowledge. Today we're diving into the subatomic realm to explore the Compton electron. A photon collides with an electron, transferring energy and knocking it askew. It's like a cosmic billiard game. The Compton effect, discovered by Arthur Compton, shows this interaction. This effect has profound implications for our understanding of the universe. In the quantum world, things are rarely straightforward. Imagine a high-energy electron zipping through a material. It knocks out other electrons like a chain reaction. These are our secondary electrons. They play a crucial role. They dissipate energy throughout the material. This affects radiation detection and electron microscopy. Hold on to your hats, cosmic explorers. Today, we're diving into delta electrons, high-speed particles that pack a punch. When a proton barrels through matter, it transfers energy, creating delta electrons. These electrons leave a trail of ionization, like supercharged bullets. In radiation therapy, understanding delta electrons is crucial for targeting tumors. Their energy distribution provides valuable insights into particle behavior. Welcome back, fellow travelers on our journey through the bizarre and beautiful world of electrons. We've encountered electrons roaming free, bound to atoms, and even surfing on waves of light. Now prepare to delve into the quantum realm as we explore the curious case of the spin-polarized electron. Electrons possess a property called spin, an intrinsic form of angular momentum. Think of it as a built-in bar magnet with a north and a south pole. In most materials, electron spins are randomly oriented. But under specific conditions, we can align these spins. This is called spin polarization. Imagine a stadium full of spectators raising blue flags in unison. That's akin to spin polarization. Hold on to your hats, folks, because we're about to enter the realm of quasi-particles. A quasi-particle isn't your average particle like an electron or a proton. It's a collective excitation, behaving as if it were a single particle. Imagine a packed dance floor. Suddenly, someone starts doing the wave. The wave travels, but it's not a single person moving. It's a collective behavior, a disturbance propagating through the crowd. That, my friends, is the essence of a quasi-particle. Get ready to push the boundaries of space and time, my friends, as we explore the mind-boggling realm of relativistic electrons. We're talking about electrons moving at a significant fraction of the speed of light, where the rules of classical physics take a back seat to Einstein's theory of relativity. Now you might be thinking, how fast are we talking? Is this like a cosmic freeway with a really high speed limit? Well, hold on to your hats because we're talking about speeds approaching 300,000 kilometers per second, the cosmic speed limit itself. As an electron approaches these mind-boggling speeds, strange and wonderful things begin to happen. Time itself slows down for the electron relative to a stationary observer, a phenomenon known as time dilation. And if that wasn't enough, the electron's mass increases as if it's bulking up for a cosmic marathon. This increase in mass isn't just some abstract concept. It has real-world implications. It affects how these relativistic electrons interact with electric and magnetic fields, giving rise to fascinating phenomena like synchrotron radiation, extremely bright and focused beams of light used in everything from medical imaging to material science. Friends, we've journeyed to the edges of the cosmos and dipped our toes into the quantum realm. Today we're plunging into the bizarre world of virtual particles, specifically, the virtual electron. In the quantum world, empty space isn't truly empty. It's teeming with a sea of particles popping in and out of existence. These fleeting phantoms are what we call virtual particles, and the virtual electron is no exception. They play a crucial role in shaping interactions between real particles. We're used to thinking of heat as the jiggling of atoms and molecules, but my friends, did you know that even those tiny electrons can get in on the action? That's right, folks, we're talking about hot electrons. Now imagine a semiconductor material. When we apply an electric field, the electrons inside get all energized, like a cosmic caffeine rush. They start zipping around with higher kinetic energy than their cooler counterparts. These, my friends, are our hot electrons. But hold on, it gets even cooler. These hot electrons aren't just running around willy-nilly. They can actually jump over energy barriers that would normally stop their less energized brethren. Think of it like this. Imagine a track and field event, but for electrons. The regular electrons are stuck at the hurdles, but the hot electrons have enough energy to clear them with ease. This ability to leap over energy barriers makes hot electrons crucial in a variety of technological applications. Welcome back, fellow explorers. Today, we're diving into the quantum world to explore the Fermi electron. The Pauli exclusion principle states no two identical fermions can occupy the same quantum state. In a solid at absolute zero, electrons stack up in higher energy levels. The highest occupied state energy is called the Fermi energy. It determines a material's electrical and thermal properties. Friends, we've journeyed deep into the quantum realm, exploring the many guises of the electron. Now we encounter the quasi-free electron, a denizen of crystalline solids. Imagine a crystal lattice, a repeating pattern of atoms. A quasi-free electron can roam this lattice, not tied to any single atom, but it still feels the collective pull of the lattice ions. This interaction influences the electron's energy and momentum. Think of it like navigating a crowded marketplace. You're free to move, but constantly bumping into others. This makes its behavior more complex than a truly free electron. We use the concept of effective mass to describe this. The electron's mass seems different due to lattice interaction. This is crucial for understanding material conductivity. The quasi-free electron unlocks material behavior secrets. And remember, this is just the tip of the iceberg. Condensed matter physics is full of exotic electron behaviors. The quasi-free electron reminds us of the quantum weirdness in solids. Let's talk about localized electrons, the stay-at-home types. These particles are confined to a specific region within a material. This confinement can arise from defects, impurities, or material properties. Imagine a pristine crystal lattice disrupted by a missing atom. This creates a potential well, trapping an electron. Think of it like a cosmic pothole trapping a traveler. The electron's wave function becomes concentrated around the defect. Localized electrons are anything but dull. Their confinement leads to phenomena like color centers in crystals. Remember those beautiful gemstones like rubies and emeralds? Their vibrant hues are due to localized electrons absorbing and emitting light. Localized electrons are crucial in technologies like semiconductors and solar cells. By manipulating these particles, we control electricity and harness solar power. Get ready for a real head-scratcher, the electron hole. It's not an electron but the absence of one. Imagine a crowded parking lot with one empty spot. That spot influences how other cars move. In semiconductors, an excited electron leaves a hole. This hole behaves as if it has a positive charge. It's like a phantom particle. Electron holes are crucial for modern electronics. They enable transistors, diodes, and more. Think about that when using your smartphone. These holes can recombine with electrons, releasing energy. The electron hole shows the importance of absence. Friends, have you ever seen a child so excited they're practically bouncing off the walls? That, in a way, is what's happening to an electron in an excited state. You see, electrons typically hang out at their lowest energy level, their ground state, kind of like how we prefer to chill out on the couch instead of running a marathon. But sometimes an electron gets a burst of energy, maybe from a photon, a tiny packet of light, and it gets bumped up to a higher energy level. Now, this excited state is like that sugar rush after too much candy. It doesn't last forever. The electron can't stay at that high energy forever. It wants to go back down to its comfy ground state, and when it does, it releases that extra energy, often as a photon, which is how we get those beautiful, colorful emission spectra. So next time you see a vibrant neon sign or a dazzling fireworks display, remember those excited electrons, releasing bursts of energy and painting the universe with light. They're a beautiful reminder that even in the quantum world, excitement is part of the cosmic dance. Okay, folks, let's talk antimatter. It's not just science fiction, it's a real thing, and it's stranger than you can imagine. Every particle in the universe, every proton, every neutron, even our friend the electron, has an antimatter counterpart. And for the electron, that counterpart is the positron. Now, the positron is like the electron's mirror image. It has the same mass, but its charge is positive instead of negative. Imagine a universe where everything is flipped, where matter is antimatter and antimatter is matter. That's the kind of weirdness we're dealing with here. The really mind-blowing thing about positrons is what happens when they meet their electron counterparts. They annihilate each other in a burst of pure energy, usually in the form of gamma rays. It's like matter and antimatter can't exist in the same space at the same time, and their meeting is a cosmic explosion of energy. So, while we haven't found any vast reserves of antimatter out there in the universe, the existence of positrons reminds us that the universe is full of surprises, and sometimes the most fascinating discoveries are the ones that make us question everything we thought we knew. Alright, imagine you're throwing a tennis ball at a wall. Common sense tells us it's either going to bounce back or maybe go over, right? Well, in the quantum world, sometimes that tennis ball can pass right through the wall. Sounds crazy, right? That's quantum tunneling. Now, electrons, despite being tiny particles, are also waves, and waves can do some pretty funky things. You see, even though an electron might not have enough energy to overcome a barrier, like the wall in our example, its wave function can extend beyond that barrier. It's like the wave is smeared out, and there's a small but real probability that the electron can suddenly find itself on the other side. This isn't some theoretical mumbo-jumbo either. Quantum tunneling is essential for many technologies, from transistors in your smartphones to scanning tunneling microscopes that let us see atoms. So the next time you think about the subatomic world, remember that electrons aren't just tiny balls of charge. They're waves, capable of incredible feats like tunneling through barriers, reminding us that the universe is far stranger and far more fascinating than we could ever imagine. Friends, we often think of solids, liquids, and gases as the main states of matter, but there's a fourth state, far more prevalent in the universe: plasma. And you know what makes plasma so electrifying? Plasma electrons. Now, a plasma is basically a gas that's been superheated to the point where the atoms are stripped of some or all of their electrons. This creates a sea of positively charged ions and, you guessed it, free-floating electrons. These aren't your everyday run-of-the-mill electrons, though. Plasma electrons are buzzing with energy, constantly moving and colliding with each other and those ions. This constant motion and interaction is what gives plasma its unique properties, like its ability to conduct electricity and be influenced by magnetic fields. Think about the sun, a giant ball of plasma. The light and heat we feel from millions of miles away? That's all thanks to the energetic dance of plasma electrons. From the auroras that paint the night sky to the heart of a distant star, plasma electrons are key players in the cosmic ballet. Welcome back, fellow explorers of the subatomic. We've journeyed deep into the heart of matter, revealing the fascinating world of electrons. Today we explore surface electrons, those restless spirits at the boundary of materials. These electrons experience unique forces, creating surface states that influence material properties. Understanding them is crucial in materials science, nanotechnology, and electronics. From the vast expanse of surfaces, we now zoom in further, focusing our cosmic lens on an even more confined realm: the edges of materials. Edge electrons, confined to the one-dimensional world of the edge, experience unique constraints. Their movement is restricted, their interactions altered, and their nature shaped by this confinement. This leads to fascinating phenomena, such as edge states and unique energy levels. These properties have far-reaching implications for novel electronic devices and quantum computers. From the boundless freedom of free electrons to the intricate dances of surface and edge electrons, we've explored a remarkable diversity in the world of these subatomic particles. We've delved into the quantum realm, unraveling the mysteries of their behavior and their profound impact on the properties of matter. Remember, the universe is awash in electrons, each one a tiny spinning charge shaping the world around us. Their story is a testament to the boundless wonders of science, a journey of discovery that's far from over. Thank you for joining us on this detailed journey through the world of electrons. We hope you found this exploration as fascinating as we did. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the wonders of science. Until next time, keep those minds curious and those imaginations ignited.